Hello, I am just recording my brief presentation about the dengue forecasting project. Um, Wanted to share my screen and talk through. I wrote this up as a Medium post with the intention of you know striking some balance between writing something that was adequately explored the topic, and also writing in a way that's accessible to people who don't spend all of their time thinking about stats and R code like some of us do. Um, so just as a little bit of introduction, the Deng AI competition was initiated by the White House in 2015. Data and sort of a mandate for how this project is executed comes from a variety of different agencies. The bulk of the data available through the Deng AI Challenge website is a lot of climate data, which makes sense because dengue fever is spread by mosquitoes, and it makes sense that a great deal of the variation in fever cases could be explained by data points that talk about how easy or hard it is for mosquitoes to live in an area. So just to talk through some of the exploratory analysis that I did, I looked for missing values. So there were a lot of missing values around the vegetation. Let's see if I can zoom in on this, around the vegetation metrics in San Juan. That was the only place where there were really a ton of missing data points. I found a really great explainer if you guys want to go to the Medium page where I wrote this and check out this link. It's a great explainer on how those vegetation metrics are taken. Sometimes so I created a flag for null values. So essentially every column has an additional column that has a 1 or a 0. 1 if the value is missing, a 0 if it's not. The rationale behind that was that there's a saying that governments love to amass huge amounts of data for people like us to analyze, but in the end it all comes down to some guy with a clipboard in the town square counting things. So my rationale for flagging missing values was that they might signal some sort of broader governance issue that could play into dengue fever outbreaks. So if the government is not good at things like counting the amounts of vegetation in the general area, or if I did the same thing with outliers. So if the government's not good at accurately writing down information, then maybe they're also not good at heading off dengue fever outbreaks. So anyways, I created those flags to incorporate into models. I ran the ggalley ggpairs plotting function on the non-flag data. So I pared down the variables to make sure that we weren't like double counting things. For example, I think air temperature is calculated from a station, from a local station, and then a reanalysis down the road. In those cases, I collapse those two variables to only look at the reanalysis ones. And then I plotted the distributions of the remaining variables here. There's not a ton that stands out to me here, except that there are a couple of these variables like dew point and air temperature have some clear seasonality, which makes sense. It's hotter in the summer and colder in the fall. And then week of year seems to be impactful, more so than any other single variable on the total cases, which also makes sense because dengue fever outbreaks are highly seasonal. So this is a decomposition, an additive decomposition of dengue fever outbreaks in each city. Again, because the virus is carried by mosquitoes, it makes sense that there would be more outbreaks when there are more mosquitoes around. So so the seasonality, I think, is reflective of that. There's a sort of 1 year between each season. There's not a whole lot to be said about trend, I don't think, except maybe there's a slight upward trend in Iquitos and a downward trend in San Juan. And then before I move on to the models, I think I've kind of yada through this, but I wanted to call out that like very early on in the modeling process, I made a decision to model these things completely separately. I think it makes a lot of sense because Iquitos and San Juan have like different climate factors that go into them, and I think if you try to predict outbreaks in Iquitos using San Juan data, you might get some different coefficients that aren't as sort of relevant. So I built out 4 models for this project, and then I built each model separately for San Juan and Iquitos. The first model I developed was an ordinary least squares regression model. So this was just a simple multiple linear regression, used the bidirectional stepwise variable selection technique to pick out 6 variables here. One of them is one of those outlier flags. So in cases where there's a lot of precipitation, the regression model, or a lot or a little, an outlier in either direction, the regression model tends to discount. Say that has a marginally negative effect on dengue fever outbreaks. The one thing that had a really high effect was dew point temperature. So when the dew point is higher, there's I guess it's easier for mosquitoes to live. So looking at the residuals of that model, there are some clear violations of the assumptions of linear regression, most notably the homoscedasticity assumption. So just about every predictor variable violates the assumption of homoscedasticity. For example, the vegetation in the southeast, this left column here. So the scatter plot in the bottom left shows the residuals plotted against the vegetation in the southeast, and the residuals are higher when that vegetation metric is lower, and residuals sort of tighten up when that vegetation number is higher. And then there's similar or inverse patterns in all the rest of the variables used there. So because of that, I didn't put a ton of effort into the San Juan least squares regression model. I basically just like ran the step step AIC algorithm again. But there was one sort of additional troubling aspect of ordinary least squares regression that I wanted to call out from this, and that is at 3 points in the timeline for San Juan, the ordinary least squares regression model actually calculates like a negative number of fever cases. So unfortunately, it is not possible to have a negative number of fever outbreaks. I think every public health official in the world would love to see that, but that's physically impossible. So so that is that's a thing that can happen with ordinary least squares regression that is inappropriate to the context of what we're actually counting. So to try and remedy that, I moved on to a negative binomial regression model. This is more appropriate for count data, particularly over dispersed count data. So Poisson and negative binomial regression models are sort of the go-to generalization of generalized linear models, the generalizations of ordinary least squares, and they're meant for count variables. I went with negative binomial because the data doesn't follow a perfect Poisson distribution. So I figured a negative binomial would be a little safer there. Again, use the stepwise variable selection algorithm to calculate the different coefficients for this. The coefficients were like very, very similar though. They were different in scale, but I think almost identical in terms of order and selection in the algorithm in the first place. One thing to point out here is that both ordinary least squares and negative binomial regression fit the seasonal trend, like the ups and downs each year. They fit that nicely, but neither model really does a great job of capturing some of these spikes where there were dengue fever epidemics. So that could be potentially problematic because I think one of the main benefits of forecasting fever outbreak is so that we can inform local medical providers that they need to stock up on whatever medicine is necessary for curing or containing the disease, or whatever practices are necessary. So fitting the seasonality is nice, but not failing to catch the spikes in the spikes in fever outbreaks is problematic. So again, I did the same residual plotting there. It's slightly better this time, and you guys can dig into that if you want. The third model I built here was the Holt-Winters seasonal exponential smoothing model. So I picked this. I wanted to do some form of exponential smoothing, and the data is not stationary. The data is not a white noise variable. So the Holt-Winters seasonal method I thought seemed more appropriate on the face of it. And what do you know? We got a nice sort of lagged fit to the data here. One of my gripes about negative binomial and ordinary least squares regression was that the data did not catch spikes, such as the late 2011, early 2012 dengue fever outbreak in Iquitos. However, there is a problem with this in that just like ordinary least squares regression, the Holt-Winters method did have some negative predictions. That's kind of a knock against it in terms of practicality and maybe out of sample validity. Again, in San Juan, the Holt-Winters method sort of fit roughly the same way. There was one negative prediction. Yeah. The last model here is is a set of seasonal ARIMA models. So I just used the auto ARIMA function in R, and for Iquitos, I came up with an ARIMA 104 model. And then in San Juan, it was an ARIMA 111 model. The fit of this data is beautiful. It really follows the trend and what happened nicely. There don't appear to be any negative predictions, which is nice, and the residuals are fairly tight. Not exactly normally distributed, but sort of definitely centered around 0. With just a few outliers around where that epidemic period happened. And then the same story is true in San Juan. So the last step here is evaluating our models. So the Deng AI competition has a mandate to minimize mean absolute error. I took that into account here, and also thought about sort of operability of the model. So the ease and the ease of deploying a model, and the negative binomial regression model performed best in San Juan by a little bit. The ARIMA model performed best in Iquitos and came close in San Juan as well. So in terms of purely minimizing mean average error or mean absolute error, I maybe should have used the negative binomial method for San Juan and the ARIMA method for Iquitos. But in terms of deploying that model, if I were to deploy the negative binomial model out of sample, I would need to also then project all of the input variables for it. And I think the uncertainty inherent in making one projection is pretty clear if you put confidence intervals on a plot of any of the projections that I've made or probably any of us have made in this class. So the confidence interval around one projection is bad. Well, not bad, but is significant, or tends to be significant. And the confidence interval around predicting 7 or 8 regressors that then forecast an outcome, a target outcome, I thought was a little too much uncertainty for me, and so I ended up just applying the ARIMA model to each city, so each separate ARIMA model to each separate city. And then the last thing I'll talk about here is the limitations and where I would like to take this in the future if we were to continue this project going forward. One of my big gripes with this data set is that we're working with a lot of climate data, and again, it makes sense that a lot of the variability in dengue fever outbreaks would be captured by factors that make it easier or harder for mosquitoes to thrive, because mosquitoes carry dengue fever. But other factors like local public health governance or public health infrastructure governance, cultural norms around using public health systems, and there's one other sort of factor I wanted to. The economics of each city. All of those would have been nice inputs, I think, and helpful inputs for this as well. So in the future, if we were to go back and do this for real for the government, or if there's a second round of this project, I would love to see some additional sort of cultural and socioeconomic data included in the data set. And then the other thing that's sort of more within my control is, if I were to do this again, I might do a more exhaustive search for ARIMA models as opposed to just using the auto ARIMA function. And then there were also, I think the prompt for this project called for 3 models, and there are more than 3 models that we've learned in this class that we could have used. So just to recap, I built 4 models. The ordinary least squares model had problems in the sense that the residuals were not normally distributed, and they residuals were related to input variables, and then also the ordinary least squares regression was making negative predictions, which is bad. The negative binomial method sort of fixed some of those problems, but then was difficult to implement down the road. The Holt-Winters model was the first model that really sort of traced all of the sort of epidemic peaks and troughs, as well as the seasonality, but that model performed really poorly in terms of mean absolute error and root mean squared error because it was lagged. So every value would have been much more accurate if it was sort of scooted up a day. But I made the analogy in my paper that the Holt-Winters model is sort of like a weatherman going on TV and saying that there's a hurricane that's about to make landfall after we've all been experiencing really terrible rain and wind for a couple of days. It's like, yeah, it's probably accurate, but it would have been nice and much more helpful if it came a couple days earlier. And then the last model was a set of ARIMA models, so one for San Juan and one for Iquitos. They were both fairly good in terms of mean absolute error and easy to implement. So I ended up submitting those for the competition, and I think I'm currently in the top 30 percentile in the competition right now. So thanks for listening. I look forward to your comments, and I look forward to reviewing some other projects as well. Thanks.